Okay. In the earlier two lectures, we covered Newton-Euler formulation and Euler-Lagrange formulation of robot dynamics. Now, in this lecture, we will see what are the practical problems with robot dynamics that we need to solve computationally, and we will see one example of development of the dynamic equations, basically following the Euler-Lagrange formulation in practice on an example. So first, what are the dynamics problems in robotics? So there are essentially two problems, one inverse dynamics problem and the other forward dynamics problem. So in the inverse dynamics problem, which happens to be easier, so this is an interesting thing in which the inverse problem is easy, the forward problem will be difficult. Okay. So in the inverse dynamics problem, the trajectory, the motion, the required motion is known, that is theta as a function of time known, and that means that theta dot and theta double dot are also known, and we have to find out the actuator torques and forces, that is output, that is effect is given, and in order to get that effect we need to find out the input or the cause. So cause is the origin, as a result you have effect. Here effect is stated, effect is given, that is this motion is wanted, for that what inputs are needed. Okay, so output given, input required, that is why it is inverse dynamics problem. This problem is required to be solved in dynamic control of robots, that is at an instant when the position is known, velocity is known, acceleration is also known from the trajectory, and therefore the long expression of the of one side of the dynamic equations can be evaluated, and that evaluation is the task of inverse dynamics. So Newton-Euler recursive equations give exactly that. Okay, at the end of it we found actuator torques and forces as the final output after the acceleration recursions forward and then force recursions backward. At the end, on the way backward, one by one we found the actuator torques. So that is what Newton-Euler recursive equations are actually designed for precisely. Euler-Lagrange approach gives the dynamic equations as expressions for the actuator torques and forces in terms of these things which are known in inverse dynamics problem. So this is also just evaluation. Okay. So inverse dynamics problem, whether we follow this approach or this approach, will be essentially evaluation. Okay. Now here it is step by step. Here it is from closed form expressions. The forward dynamics problem is more complicated. So here the problem is, given the proposed expressions for actuator forces and torques, that is, suppose we give the robot actuations according to this function of time, essentially tau of time, t, because theta, theta dot, theta double dot are also finally functions of time only. So if at time t equal to 0, 0.01, 0.02, 0.03, 0.04, if we follow this control law, that is this torque we propose to give to the robot, then as a result of that, what motion will result. Okay, so in this case, input, the cause is given and output required. This is the effort, what is the resulting motion, what will be the resulting motion if we give this input. Okay, so that is why it is forward problem, cause given, effect wanted. So this is useful in simulation of control laws. That is, we have designed a control law, and before applying it on the robotic hardware, before applying it on the robot itself, we want to computationally find out what will be the resulting motion of the robot. Simulation means that actually. Okay. Simulation literally, original sense of simulate was to nod your head. That is in support. So whatever way the actual system would behave, to find out that through mathematical modeling, that is basically computer simulation of any system, whether robot or nuclear power plant or whatever. So this is important in simulating control laws. That is, after designing control law, you numerically simulate how the control law will operate in actual motion of the robot, and for that you will need to solve differential equations. How to organize the equations? Let us see that. The process. First, organize the dynamic equations in state space, because dynamic equations are second order differential equations, and the computational process for solving differential equations is straightforward and systematic for first order equations. So typically, any initial value problem, any simulation problem, when you need to solve, you essentially convert that to first order equations first. And that is very easy. Conversion of dynamic equations to state space is very simple. You take the state vector as theta theta dot. That is one bunch of state vectors, that is x1 vector, and the second bunch of state vector theta dot, which is x2. Okay. So if the robot was n degrees of freedom, then state space dimension will be 2n. Now, in state space, you have position and velocity up to first order derivative, because the dynamics itself is second order. Okay. So the second order derivative you cannot include in state. That will come from the dynamic equations. Let us see how. Now, for the first order equations which we see, you will basically take these as the unknown functions x. Okay. So x1, x2, x3 up to x2n. Okay. So it's dot you find out, and there is nothing to find out, just organize. So that will be x1 dot x2 dot. X1 dot will be theta dot, x2 dot, x2 is theta dot. So x2 dot will be theta double dot. Now theta dot is essentially x2. So x1 dot turns out to be x2. Okay. So that is x2. Theta double dot, this you will get from the dynamic equations. So x2 dot, which is theta double dot, that is the applied torque minus all the dynamic equation terms, this one, this one, this one, except the inertia term, m into theta dot, double dot. Okay. So just leave m into theta double dot on one side, take everything on the other side. So tau minus all the rest of it. And now this rest of it, this whole thing, tau minus this rest of it, that turns out to be m theta double dot. So pre-multiply with m inverse, and then you get theta double dot. Okay. So this is x2, and this also is eventually function of t and x1, x2, because whatever is inside this is basically function of x1, x2 and time. Time because tau comes as a function of time. So this is function of theta, which is basically x1. This is theta dot, which is x2. This also is function of theta, which is essentially x1. This is also function of x1. This is also function of x1 and x2. So finally, you have got x dot as a function of x and t. And that is the standard form of first order differential equations for solution with a computer program. So this is a system of 2n first order ODEs Now, when you simulate a system, you need to tell the governing equations, the laws that govern that system, which is here. Okay, the rate of change of the state variables, and you have to give the current state. So state vector was x, so theta theta dot. So the current state, present state, will be theta at this time and theta dot at this time. So theta 0, theta dot 0. These are the initial conditions. So use these initial conditions, these values you know. So with these initial conditions, initial values, and these dynamic equations organized in state space, you basically set up an initial value problem, IVP. And then solve this IVP. Basically, you use Runge-Kutta fourth order method or Runge-Kutta-Fehlberg fourth and fifth order method or some such equivalent method to solve the differential equations. The output, the result of this initial value problem solution will be x of time at various time instants after 0, the x values will come. That means the 2n values for every time instant. Okay, so the first n of them will give theta and the next n will give theta dot. Okay, so at the time of solving an initial value problem, you need to mention that is t0 to this final time we are solving an initial value problem. To solve this problem, this computation problem, there are enough library subroutines. MATLAB also has very good functions. ODE45 is the function that uses this method. Okay, so through this you can figure out how the robot will behave if this control law is utilized. If you are happy with those numerical solutions, then you will try it in the robot itself. If you get unexpected, very funny behavior of thetas and theta dots with time, then you don't trust this control law. So that is the purpose of simulation. Now, we take an example. Not of this, but how to develop the dynamic equations. Okay. A simple 2-hour planar robot we take. This has come very faint. That is very unfortunate. So this is first link, this is second link. First link is of length L1, second link is of length L2. First link is at position theta 1, second link is at position theta 2. That means inclination of the second link from the x-axis turns out to be theta 1 plus theta 2. The same setup that we used for the kinematics. Now, in the link, first link, the center of mass of the first link is at C1 distance from its pivot. Center of mass of the second link is at C2 distance from its pivot. Okay. And here you would note that I have put the center of mass of each link centrally along the axial line. Here also, here also. That is not necessary. It is possible that it is a little off the center. So in that case, here rather than theta 1, it will be theta 1 plus that constant angle. But that will not add much extra complication. Now, the position of this point, the center of mass, is PC1. That is simply this distance C1 into cos theta 1 sin theta 1. Position of this will be is L1 cos theta 1 sin theta 1 plus addition C2, this vector, C2 cos theta 1 plus theta 2 sin theta 1 plus theta 2. This is simple position kinematics which you have done. Now, its derivative will give us the velocities. The velocity of C1 is the derivative of this. That will be minus C1 sine theta 1 dot, then C1 cos theta 1 dot, like this. And the velocity of the center of mass of the second link, this one, will be its derivative. So you differentiate this L1 times minus sine theta 1, that is why it's minus sign outside, into theta 1 dot, plus C2 into minus sine theta 1 plus theta 2 into theta 1 dot plus theta 2 dot. So it is here also. Similarly, the other coordinate gives this derivative. Sine derivative is cos everywhere. So the velocities of these 2 points you have found. CM, center of mass of this, center of mass of this. And now the square of this velocity is very simple. C1 square theta 1 dot square. Square of this velocity is a little complicated, but such things you have done in kinematics enough. So basically this has theta 1 dot terms and theta 2 dot terms. So in the square, basically we'll square this and square this and add them, right? And you will get 3 terms, theta 1 dot square, theta 2 dot square, and theta 1 dot theta 2 dot. So in theta 1 dot square, the final terms will come very simple, because from here and here, 2 terms will come together and give you L1 square. From here and here, 2 terms will come together and give you C2 square. And 2AB of these two will give you twice L1 C2 into cos theta 1 plus theta 2 cos theta 1 plus sin theta 1 plus theta 2 sin theta 1. That basically means cos theta 1 plus theta 2 minus theta 1, which is cos theta 1, cos theta 2, okay, into theta 1 dot square. So this is theta 1 dot square term. Theta 2 dot square term will come from this square plus this square, which is simply C2 square theta 2 dot square. Theta 1 dot theta 2 dot terms will come from twice this, and twice this. Okay. So in each of them, there are 2 terms, because here there are 2 terms. One term will come from this, one term will come from this by their product with this. So here twice L1 C2, twice L1 C2, the same cos A cos B plus sin A sin B. So that is cos theta 2. And the other term will come from this and this. So here also C2, here also C2. So 2 C2 square cos square plus sin square. So basically 2 C2 square. This is with theta 1 dot theta 2 dot. So Vc2 square also you find. And then kinetic energy of the first link, that will be half m1 velocity of Cm square plus half I1 about the center of mass into omega 1 square, right? So half mv square plus half I omega square with subscript 1, that is for the first link. Okay. So from here you take Vc1 square, put it here, and omega 1 is essentially theta 1 dot, so put that also. So add them together and you get half I1 plus m1 c1 square into theta 1 dot square. So you see, we did not apply parallax theorem of a moment of inertia, but that has come on its own. Okay. So this means if we had not considered the angular linear motion of the center of mass and angular motion separately, like in these 2 terms, rather if we had said that the link is rotating as a rigid body about its pivot, so transfer the moment of inertia from the Cm to this pivot, that would basically mean I1 plus m1 c1 square. Okay. So it would mean the same thing. Okay. Then kinetic energy of the second link, that will be half m2 vc2 square, this one, plus half I2 omega 2 square. Omega 2 happens to be theta 1 dot plus theta 2 dot. That is angular velocity of the second link. So this. So half m2 vc2 square, this whole thing, whatever we have evaluated, plus half I2. In place of omega 2, it is theta 1 dot plus theta 2 dot. Okay. So then you add up these two things for the kinetic energy of the total complete robot. So when you add these two things, you collect the terms together, theta 1 dot square, theta 2 dot square, and theta 1 dot theta 2 dot. Okay. So after step-by-step process, you will get an expression of this in which m11, by collecting all the theta 1 dot square terms from here and here together, you will get the coefficient of theta 1 dot square, whatever it comes out, will be half into this thing. Okay, this you should take your time to verify. Similarly, you find out the total coefficient of theta 2 dot square in this and this, and the twice of that will be m22, that will be here. Okay, and then similarly find out the theta 1 dot theta 2 dot term together, and that coefficient you make m12, which will be the same as m21. So this is m21, and the same expression here. Here this dot 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 is essentially this thing. Okay, this parenthetic term, because it is a symmetric matrix. So you develop the inertia matrix, and that means the kinetic energy like this. Okay, and then you work out the potential energy. Potential energy is easy. mgh of the first link, for height you get yc1. Okay, plus mgh for the second link. Here for h you get yc2. G is common, keep G common. M1 into yc1, M2 into yc2. So yc1 is this c1 sine theta 1, yc2 is this second component, second coordinate. Okay, so put those things. This is m1 yc1, this is m2 yc2. Okay, so this is the potential energy, and you have got both kinetic energy and potential energy, and now it is the all those differentiations. Work out the Lagrangian, and then for the first dynamic equation, you start with del L by del theta 1 dot, which is essentially del K by del theta 1 dot, because U does not depend on theta 1 dot. So del K by del theta 1 dot, look at here. When you partially differentiate this with respect to theta 1 dot, you get one term from here, m1 theta, m11 theta 1 dot, and one term from here, m12 theta 2 dot. Okay, that is this. And then you differentiate this with respect to time, and that will give you m11 theta 1 double dot plus m12 theta 2 double dot plus time derivative of m11 into theta 1 dot plus time derivative of m12 into theta 2 dot. These two will take some effort. Okay, so these two are straightforward. M11, M12 expressions we have, they will just come. Here, M11 has to be differentiated with respect to time. So M11 is here. Okay, this has theta 2, which is a variable. So basically, to get its time derivative, you have to differentiate it with respect to theta 2 and then multiply with theta 2 dot. And so that will be twice L1 M2 C2 into minus sine theta 2 theta 2 dot. So minus twice L1 M2 C2 sine theta 2 dot, and this theta 1 dot is here. Okay, plus this one M12 has to be differentiated with respect to time and multiplied with theta 2 dot. So M12, which is same as M21, see it here. This is also dependent on theta 2. So you have to differentiate it with respect to theta 2 and then multiply with theta 2 dot. So what you get? L1 M2 C2 minus sine theta 2 into theta 2 dot. So minus L1 M2 C2 sine theta 2 dot, and another theta 2 dot already sitting here. So square. Okay. So this is the derivative that you have got. And now from here we have to subtract del L by del theta 1. Okay. Which will be del K by del theta 1 minus del U by del theta 1. Here both terms will contribute. Del K by del theta 1 minus del U by del theta 1. Del K by del theta 1 is 0, because as you saw just now, K is this, in which there is no theta 1. These three fellows could have had, but here theta 2 appears, not theta 1. So this derivative is 0. Del U by del theta 1 is there. Del U by del theta 1. So theta 1 is here. So from here you will get G times M1 C1 cos theta 1. And this is partial derivative, so theta 1 dot will not come. Theta 1 comes here also, okay. So from here you will get M1 C1 cos theta 1. From here you will get M2 L1 cos theta 1. From here you will get M2 C2 cos theta 1 plus theta 2. So three terms. M1 C1 cos theta 1, M2 L1 cos theta 1, and M2 C2 cos theta 1 plus theta 2 into G. Fine. So keep that. Now you have got del L by del theta 1, and above here you got this term. Now for the dynamic equations, you have to say this minus this is equal to tau 1. So get this whole thing, the last line, minus minus plus, this whole thing is equal to tau 1. So the first dynamic equation turns out to be that. That entire thing that we earlier got by differentiating with respect to theta 1 dot and partially then with respect to time, from that we subtract this, so minus minus plus, this bracketed thing totally comes here, and that is the first dynamic equation, expression of tau 1. Okay, inertia term, this is coupling inertia, that is a theta 2 double dot also reflects in tau 1. Similarly, in equal amount, a theta 1 double dot also will reflect in tau 2. Okay, because M12 is M21, same. Then Coriolis term here, centripetal term of the second one. Okay, because second one is also supported by first link, first torque. And then the gravity term. In addition, if there are viscous friction and Coulomb friction included, then those terms also will come. Okay. Then in the similar manner, all the steps you take for the second dynamic equation. Del L by del theta 2 dot, which is del K by del theta 2 dot, which will be this. From here, with respect to theta 2 dot partially. So it will give you M12 theta 1 dot plus M22 theta 2 dot. That's all. Then you have to differentiate that with respect to time. That is this with respect to time next. That will give you m12 theta 1 double dot plus m22 theta 2 double dot plus m12 dot theta 1 dot plus m22 dot theta 2 double dot. This one will turn out to be easier, okay, because in the second column or second row of the inertia matrix, expressions are simpler. So these two terms are as they are, and here m12 dot or m21 dot, whatever. This dot. We have done it once earlier. So that will be minus L1 M2 C2 sine theta 2 into theta 2 dot. Okay. Minus L1 M2 C2 sine theta 2 into theta 2 dot. And theta 1 dot is already sitting here. So get that. Plus M22 dot is 0 because M22 is constant. Okay. So that's all. This term is easier. So then differentiate it with respect to theta 2. That is del k by del theta 2 minus del u by del theta 2. So del k by del theta 2. It depends on theta 2. Okay. Several terms. This one and this one also. Okay. It depends on theta 2. So now this time it is partial derivative with respect to theta 2. So that will be simply twice L1 M2 C2 into minus sine theta 2. Here it will be L1 M2 C2 minus sine theta 2. So here it is twice and here it will be 0. Okay. So appropriately you take them there in the derivative. So this part will be half this theta 1 dot square plus this half this theta 2 dot square plus this theta 1 dot theta 2 dot. This one turns out to be 0 because m22 is constant. It does not depend on theta 2. This one gets you twice whatever we found minus L1 M2 C2 sine theta 2. And there is a half with that. So my half and twice cancel out and this remains with theta 1 dot square. Here that twice does not come, but here there is no half either. So it turns out to be the same coefficient. So the same coefficient with theta 1 dot theta 2 dot. And this one is 0 because m22 is constant. Minus the del u by del theta 2 that gives you this because in the expression of u, you have only theta 2 dependence here. Okay. Everything else is theta 1. So g times m2g times c2 cosine theta 1 plus theta 2. Partial derivative. So that's it. m2 c2 cosine theta 1 plus theta 2. This minus sign is because of this minus sign. Okay. And now the difference of these two is tau 2 according to the Lagrangian formulation. So subtract from here this thing and then you get tau 2 equal to m12 theta 1 double dot plus m22 theta 2 double dot. Now this term and this theta 1 dot theta 2 dot term here just cancel each other exactly. Okay, so that is gone. Then minus this whole thing. So minus minus plus L1 M2 C2 sine theta 2 into theta 1 dot square. This remains minus minus plus M2 C2 cos theta 1 plus theta 2 G. This remains. So this is the second dynamic equation. Okay. So that first boxed item that we had here, which is more complicated, that makes sense because the first actuator has to support not only the first link but the second link also. Second actuator has to support only the second link because that is later. That doesn't have to bother about supporting the first link, though the inertia coupling is there. Friction terms, as applicable, may be separately added. Typical models for terms associated with viscous friction is minus a coefficient times theta I dot in the expression for tau I, and for Coulomb friction minus its coefficient into sine of theta I dot. Okay, because if theta I dot is positive, then it will be negative Coulomb friction. Okay, and if theta I is decreasing, then this will be positive. So this minus sign minus sine of this. So it will be either plus or minus depending upon whether theta I dot is positive or negative. So this term for Coulomb friction and this term for viscous friction may be added to the tau I expressions above. Okay. So this is how you develop dynamic equations. Now for another manipulator, you can try out to develop the dynamic equations on your own. Okay. And see the examples and exercises in the book also, how these are developed. Okay. So this completes our study of robot dynamics. And after this, the lectures on control, robot control will be given by Dr. Bhattacharya. Thank you.